Welcome everyone to this latest installment of the MP seminar series. My name is Janosch. I'm a Materials Project staff member, and I'll be making a few opening remarks before handing it over to Julie. So since there's been a 6-month hiatus, I'd like to reiterate the format of this series. Going forward, we'll resume our original cadence of roughly bi-monthly talks from both top researchers as well as early career scientists. And if you know someone whom you'd like to nominate as a future speaker, including yourself, please visit materialsproject.org/seminars, where you'll find a form to submit suggestions. This talk will be recorded and later uploaded to YouTube, so we therefore like to keep the talk uninterrupted. If you have any questions, just use the Zoom Q&A button in the bottom toolbar to submit them, and we'll get to as many questions as we can at the end of the talk. We also set up a discussion forum for this talk at matsci.org/c/49, where you can post any questions that we didn't get to or that occur to you after the talk. You can also find that link in the chat of this Zoom meeting. And finally, if you'd like to review any part of this talk later, you can, like I said, visit our YouTube channel where we'll upload this recording a few days from now. And with that said, let me introduce today's speaker. Julie is a professor of material science and engineering at MIT. He has previously held faculty positions at Ohio State University and the University of Pennsylvania. His group investigates the mechanical, electrochemical, and transport behaviors of materials to find new methods of energy conversion and storage. Ju was elected Fellow of the American Physical Society in 2014. He became a Fellow of the Materials Research Society in 2017 and a Fellow of AAAS in 2020. So today we're very excited to hear from Ju about the development of a universal interatomic potential. And without further ado, I'll stop sharing my screen here and hand it over to Ju.
Okay, it's a great pleasure to speak at the Materials Project seminar. I use Material Project every day, pretty much. I'm a great fan of what you do there. So I'd like to start by saying that we have this universal gravitational potential which explains the trajectories of celestial bodies, and is clearly key for understanding materials behavior in case of atoms as well. And the Nobel Prize in Chemistry was awarded to Walter Kohn and John Pople for basically coming up with the ground state energy for collection of nuclear positions by solving the electronic structure problem on the fly. But this is quite expensive with something like at least into the cube scaling with plane wave basis. So when we try to deal with realistic microstructures, so what you see here is a lattice dislocation being absorbed by a coherent twin boundary. So in all kinds of materials problems, we need to deal with tens of thousands of atoms, and it's not sufficient to use the ab initio potential. So generally, we use so-called empirical potentials, and there has been a lot of good work in this field. For example, this OpenKim database was really important for the community. And about 2007, Baylor and Parnello came up with this new network interatomic potential, where they basically have a two-layer new network with a hyperbolic tangent as the activation function, and they generated 9,000 DFT configurations. And what is truly amazing about this paper when I first saw it was the error. So it's 5 milli-electron volt per atom, which is much lower than the so-called chemical accuracy, which is 40 MeV per atom, the typical sort of error bar in thermochemical measurements. And nowadays, as shown by this review, very good review, we actually have a range of machine learning potentials. And the neural network potential actually is not the most competitive one for simple systems. So in this case, the horizontal axis is the effective computational cost. And then the vertical axis is the testing error. And actually the most accurate but expensive method is, according to this review, is a Gaussian approximation potential, the gap potential. And then the new network potential is this red circles, and then the SNAP, which is spectral neighbor analysis potential, are these yellow circles, and the Q-SNAP are these green circles. But in a lot of the computational cost and error, the Pareto front is actually this moment tensor potential, MTP potential. And this is a comparison with well-known potentials, embedded atom potential, modified embedded atom potential, the Tursov potential for pure nickel, copper, lithium, moly, silicon, germanium. I think this is some kind of mean average error. And what you see is that, and this sort of conforms with my experience when as a grad student using these potentials, that you're dealing with really huge hundreds of MeV per atom errors. But once you switch to these machine learning potentials, then you have at least an order of magnitude improvement in these energy errors. However, I just want to say that most of the machine learning potentials today are for non-atomic binary or up to maybe 4 or 5 elements. We did a survey in like how many potentials are in the open KIM database for, let's say, more than 3 atoms, and it's like less than 1% of the potential. So in the early days, we have collaborated with Professor Tim Kaxia's group in developing kind of Baylor type potentials for specific systems, such as sodium chloride or lithium fluoride, beryllium fluoride, molten salt systems. So for example, here we have 2 hidden layers, and we're using the Baylor approach, which are these radius dependent and angle dependent symmetry functions. And generally we fit the forces, we fit the total energy, and we also do some regularization to prune out some of the weights. And so here you see that we have these radial symmetry functions, we have these angle dependent symmetry functions, and these are our training data sets. So we've got high temperature crystals, 0 temperature crystal, a lot of normal liquids, but very high temperature liquids like 5,000 degrees, compressed liquid, and then gas phases like dimers, and then some crazy non-stoichiometric ionic systems, and so forth. And so total is about, in this case, 100,000 configurations. And we also treated very short-range interactions so they don't collapse. And in the DFT calculations, we have van der Waals interactions. And we are able to reproduce kind of similar results as what other people have obtained, which is the testing error is on the order of 1 to 2 MeV per atom. And then the force error is a 0.04 electron volt per angstrom. And just want to say that, so we are able to fit, therefore, DFT much better than DFT can represent reality, because DFT is known to have above the chemical accuracy kind of error, typically 2 chemical accuracies, like 100 MeV per atom. So as far as the goal of the machine learning potential, this kind of fulfilled the target. And then we use it to do, for example, high temperature molten salt. And we were told, actually, when we compare with neutron scattering measured radial distribution function, that actually some of these are experimental artifacts. So the experimentalists told us, this is actually pretty good agreement. And we fit the equation state for the liquid phase. We can fit things like thermal conductivity, mass diffusivity, heat capacity. And I just want to say that our goal is not to reproduce the experiment, because DFT itself have some error. And so our goal is really to show we can reproduce the DFT data. And for example, here we have different point defect formation energies, different surface energies, elastic constant. So the normal stuff you would try to fit empirical potentials, melting point, and so forth. And then we also generalize this approach to lithium fluoride. Again, similar kind of energy errors on the order of 1 to 2 MeV per atom. And then the surface energies are pretty good. These are not fitted, these are predictions. And also just want to comment that the DFT surface energies are well known to actually have some error compared to experiments. So then we look at these kind of ternary salt, which is using fusion energy as the coolant and also as neutron breeders. So we look at high temperature liquids, crystals, and generally we do quite well compared to DFT calculations. So switching gear a little bit to metallic systems. So we have also used this kind of neural network potentials to fit a well-known kind of a tough case, which is the nickel titanium shape memory alloy. And the reason it's a tough case is because at 0 temperature, these three phases, B2, B19 prime, B33, are very close in energy. In fact, the room temperature stable phase is a phonon unstable at 0 temperature. And so it's really stabilized by the vibrational entropy effect. And by doing new network fitting, we're able to pretty much reproduce the basic properties of these competing phases. And the key is the phonons, as I mentioned, because these are the vibration entropy is a very key part. And there was previously an MEM potential. And this modified embedded atom potential is able to reproduce the imaginary phonon frequency at the endpoint, comparing with the DFT density functional perturbation theory calculations. But it's not able to capture another phonon instability branch between the gamma and R point, so in R direction. Whereas the new network potential, without intentionally fitting this particular phonon, we are able to reproduce this phonon instability. And so what we have done is a potential mean force calculation to get the finite temperature free energy. So at 0 temperature, B2 is a phonon unstable. So actually B19 prime is the locally stable, actually globally stable phase. But as we raise the temperature along the reaction coordinate, we compute the average stress, which is the generalized force in this phase transformation, and we integrate this average thermally averaged force. And so at some temperature, which is about 380 Kelvin, we reach the first order phase transformation, and then B2 phase is stabilized. And this was really difficult to reproduce with previous potentials. The experimental observation is something like 40 Celsius. So the error is not too great. And then when we run the MD simulation, right away we found some very interesting features. So typically when you have a twin boundary, a symmetric twin boundary, you would have a highly coherent twin boundary. But in our case, we found that near in the MD simulation, we have this reconstruction which goes into this B19 prime-like structures. And the grain boundary actually have this kind of a curvature, which is highly unusual. And that actually turns out to have experimental kind of validation. So this is a TEM experiment where people find B19 prime-like domains on the twin boundary of B2 in the B2 phase. So even though B2 is the globally stable phase at a particular temperature, because of these near boundary motifs, these are highly glissal and give you very low hysteresis, pseudoelasticity, and shape memory effect, because you actually have a pre-existing nuclei that's always living on these boundaries, that's ready to be activated. And so we have also seen that we can do thousands of atom simulations, and in this case, loading this nitinol nanowires and see this pseudo-elastic phase transformation, where when you unload, it goes back to the original strain. Okay, so that's actually just sort of the intro to how we come to think about new network potentials. So what we sort of set out to do when So Takamoto, who is my a visiting scholar from University of Tokyo, when he visited my group for a year, what we set out to do is really to aim at chemical complexity. So our initial ambition is just to be able to reproduce high school chemistry. By that I mean, there are certain very basic chemical facts, like if you throw a piece of sodium metal into liquid water, you should get hydrogen gas out, hydrogen gas bubbles. If you throw a piece of sodium chloride into water, it should dissociate. You should get sodium cation surrounded by a solvation shell, and the chloride anion surrounded by a solvation shell. If you freeze liquid water, you should get ice, which float on top of water. So very basic things like that should come out of direct MD simulations. So things that, what we learned at high school, it should just get out of MD simulations. And we're not really going after the accuracy per se, but really the trends in chemistry. And so we set out to develop this called the Tensor embedded atomic network. And we end up with half the chemical accuracy, which is about 20 MeV per atom for the first 18 elements on the periodic table from hydrogen to argon. And one sort of unique thing about this is how we train the model. We do not bring any a priori chemical intuition into the fitting. We actually really randomly throw all these elements together in the simulation box. So no pre-existing crystals, because we just don't want to bias the new network. Because if you bias the new network, very often what happens is it hallucinates. In other words, it could dream up, like if we don't, tell it that, when you have argon bonding with carbon with chlorine, which is a very unlikely situation. But if you don't tell the new network that energy for this is very high, then it could actually dream up of an argon bonding to 4 carbon and 1 chlorine, right? So in the training, we really have just randomly throw these atoms together. And the other thing that we need to pay attention to is this issue of equivariance. And so this is well known in image recognition that, let's say, if you have a convolutional neural network that recognizes BMAP 3, now if you rotate this image, you really should still recognize 3. So it's the same for molecules, that if there is a rotation, we should still give the same energy. And the previous architecture, let's say using the graph neural network, for example, the beta potential is just to pass scalars. If you pass scalars, then you're always going to be rotational invariant. But then there are also architectures such as Cormorant and Equip, which use spherical harmonics. In our case, we use general tensors. In other words, rank 2 tensors, we could use also rank 3, rank 4 tensors, rank 1 tensor, which is vector, as well as scalars. So we use, for the first time, all scalar, vector, and tensors, and we assign them to atoms as well as to bonds. And really, the tensor language was actually invented to guarantee equivariance. What he says is that pretty much every physically well-defined quantity should be represented into tensors. When you undergo a rotational transform, it must transform by this particular tensor contraction law. In other words, when you tilt your head and you measure the same physical quantity, the numbers would change, but it should still be the same physical quantity, and therefore it must satisfy this relation when you undergo a frame rotation. So as long as you just follow this tensor Einstein notation, so you can construct a rank 4 tensor by doing a generalized dyad of 2 rank 2 tensors. Or if you do, let's say, dummy index summation, you contract a rank 3 tensor with a rank 2 tensor, get a vector. So basically, as long as you follow the Einstein index summation convention, you're guaranteed to have equivariance. So to show you what it looks like, for an atom, we could have 16 vectors. So these would be 16 by 3 in the memory. We could have 128 scalars, but we could also have 16 matrices which are attached to the atom. So this would be 16 by 9 in the memory. And then we basically distribute the atomic centric scalar vector tensor to bond. Bond also have its own bond vectors and bond tensors. And so we go also from bond to atoms. And the motivation for this is really coming out of sort of this tight binding approach. So in the linear combination of atomic orbitals, you construct this electronic Hamiltonian, where these are the matrix elements. So for example, this is trying to represent the band structure of silicon carbide using 1s orbital, 3p orbital, 5d orbitals, and an excited s orbital. And you construct this 20 by 20 Hamiltonian matrix, where let's say this submatrix, when you rotate your head, you're going to redefine your d orbitals, and then these matrix would rotate according to the tensor transformation laws. And so the idea is that if we think about a general electronic structure calculation, this is, we have atom and bond-centered scalars, vectors, and tensors. And of course, they have their nonlinear interactions in the neural net. But this is similar to constructing an electronic Hamiltonian, which is tensorial based on the atomic positions. But then when we are doing this self-consistent tight binding calculation, let's say you do DFT with minimal basis, then you would do this charge iteration. So all we do is we concatenate the same architecture 16 times in our initial TeaNet formulation. And the goal is to mimic how physical quantities are supposed to flow in a self-consistent electronic structure calculation code. Although inside it's entirely empirical, but we're going to output this final scalar, which is the total energy. And I'm not going to bore you with the architectural details. It's all written in this computational material science paper, but it's just like a lot of architectural engineering in this. But it does sort of have an intellectual sort of interesting problem, because we're always limited by memory. So let's say you would like to assign 256 floating point number. You want to assign this attribute to a particular bond. You can either have, let's say, 166 scalars to the bond, let's say bond length and other bond quantities, plus 30 vectorial quantities. Or you could have only 20 vectors, but 6 T2 matrices, which takes 6 by 9 numbers. And you can even have a particular rank 3 tensor. And a characteristic rank 3 tensor is like piezoelectric tensor, where you look at how much the dipole would change upon some kind of strain. So there are definitely physical effects that you can sort of define on bonds which are of this type of architecture. So there is sort of a question of, when you do the let's say, architectural tuning, how you do this kind of memory asset allocation in this. So this is what we got when So was at MIT. So we were able to reproduce hydrocarbons, so acetylene, acene, ethane, benzene, so their properties, and then crystalline sodium, aluminum, silicon. And then these are the different polymorphs of SiO2, silica, quartz, alpha quartz, cristobalite, tritamide, and some amorphous silica. This is water. So we have a chloride ion with a solvation shell, and then also a hydronium ion. And what is really interesting is this so-called number of atomic pairs matrix. Just to show you, we're really just randomly throwing stuff in the DFT box. Because you see that we have, argon interacting with chlorine, argon interacting with aluminum. So, you can see, so what this is basically in all the DFT calculations we have generated, we just look at the number of nearest neighbor pairs, and this is the sum of the occurrences of, let's say, fluorine-argon pairs in our DFT database. So, we really have a lot of crazy chemistries in our fitting database, but we do think this is necessary to prevent sort of hallucination of the neural network. So our goal was really to, do the whole periodic table. So the point is that we're able to do this all with the same neural network. And so So went back to Japan. He joined the leading AI company, which is a preferred network in Japan. And he put together a big team of developers, and we basically generalized this to the whole periodic table. And in this Nature Communication paper, they show the 4 examples: lithium cation diffusion in this cathode material in lithium-ion batteries, molecular water absorption in metal organic frameworks, MOF74 with different metal centers, order-disorder transition in binary copper-gold alloy, and then synthesis of hydrocarbons by Fischer-Tropsch synthesis using hydrogen gas and carbon monoxide based on these multi-metallic catalysts. So the point is that typically, previously, we usually do one problem by developing a particular, let's say, neural network or machine learning potential. We publish a paper on that. So what this paper shows is that you can use the same potential with quite consistent errors and heteroformations, and you can just arbitrarily do all these different chemistries. And generally, the error that we have is similar to TeaNet, is on the order of half of the chemical accuracy, sometimes actually much better than that. The computational efficiency is like this. So if we do a 3,000 platinum atoms, which is just like a 4 nanometer, 5 nanometer cluster of platinum, then with DFT, it would take a century if you do the standard plane wave DFT. But with PFT, it would just take an hour of computation. And the newest version 4 release is now covering 72 elements. And I've been asking them to do the actinides as well, because I'm in nuclear engineering and we care very much about actinides. So it's going to happen. And in developing this potential, they have used more than 1,000 GPU years of DFT calculations. So that's GPU millennia of DFTs. And also, we have used active learning, which is we always try to automatically find where the PFP is disagreeing with the DFT result. So it's sort of very self-critical. And it actually actively look for regions in the chemical space where there is bigger error, and then try to generate more configurations. in those bigger error regions. So the active learning-driven sampling have now generated more than 22 million configuration, which is already much bigger than when the Nature Communication paper was published. And we have compared with the catalysis data sets with SHNet, DimerNet, etc. And generally for disorder structures is a bit higher in error. But generally the point is that we're able to fit DFT quite better than what we know that DFT can represent reality. So we're kind of reasonably satisfied with the framework itself. So what this will enable us to do is to study microstructures. Because traditionally when you do DFT, if you do a grain boundary or surface, it's typically like a flat, or if you do a dislocation, it's like a straight dislocation core. Now we can study dislocation-dislocation junctions. We can study curved dislocation, curved interface interactions. We can study realistic phase transformations with heterogeneous nucleations, plasticity, damage, evolution, things like stress-corrosion cracking, electrochemical interfaces, and so forth. And we have been working very hard on representing the Fondang properties well. Fondang is a bit tricky because it's like a second derivative of the energy. And sometimes the neural network have noises. And so to get the second derivative right actually takes some effort, but we're able to represent these quantities. And now we're also trying to get to the charge density because so far the architecture has been, let's say, medium range, but we are kind of developing long-range interactions, and to be able to handle long-range interactions, we first have to get representation of the electron charge density, and we are making good progress in that. So that will lead to electronic transport, things like electron phonon coupling and so forth. So to show you some initial applications, so this is a new salt for aqueous zinc-ion battery material. So zinc-ion battery, zinc metal battery have this hydrogen evolution problem because the zinc metal potential is actually below the hydrogen evolution potential. So what people have developed experimentally is this benzene sulfonyl benzene sulfonamide anion, which is an amphiphilic anion. So it has a hydrophilic part, the core, and then have two hydrophobic sides. And so when we do this electrochemical interface, what we found was that this zinc BBI salt sort of have a very strong tendency to form almost like a solid electrolyte for zinc ion near the zinc metal. And also this is conducting to the zinc cation. So the zinc cation is able to transport across this, let's say, self-assembled SEI, if you will, although this is not permanent. If you remove the electrode, it's going to go back, redissolve into the water. But it actually is hydrophobic and it sort of not allowing the proton to contact the zinc metal. And that sort of is the key insight, which is you need to have this quote unquote electron insulating, so electron cannot tunnel, and also proton phobic self-assembled layer, which nonetheless is still a good zinc solid electrolyte. We're also starting to do some crystal structure evolution with this empirical potential using this USPEX-like algorithm, where you have an initial population of crystals, you sort of hybridize, you cut them into two pieces, marry them, and then generally sort of keep a constant population of these after energy minimization, and you do the new transmutation. So a sort of a sanity check, if we start a simple cubic structure for carbon, we do this structure evolution, we're able to get diamond and graphite. If we do silicon, we're able to get silicon diamond cubic structure. Iron, we start from simple cubic, we're able to get body center cubic. Sodium chloride, start from tetrahedral structure, get rock salt structure. Tantalum oxynitride gave us something pretty reasonable compared to experiment. So we start to see, can we expand upon the materials project structures? So what we do is we take the structures in the ground state in the materials project, and then we run the PFP potential, and if we also have a PFP convex hull, which is not necessarily the materials project hull, but after we found some new structure which breaks the PFP hull, we then calculate with GGA. We can only do GGA because our PFP is fitted to GGA, so we cannot, we should not run other potential, because when our PFP only supposed to reproduce GGA. So at least in the GGA hull, we're able to break the GGA hull in this lithium-3 nitride case. So this is calcium phosphide, and by evolving with variable compositions, we actually was able to find, we first break the PFP hull using the initial structures that we get from materials project, but then after we break them, like here, these crosses, we verified that they actually also do break the GGA energy hull. So this is ongoing. We can sort of get like about 1,000 new structures for like 3 hours of running time. And we can do pretty big structures. I think I'm going to skip over this. So we are looking at molten salt corrosion, which is molten salt is used in advanced nuclear reactors as coolant, as breather, but it's also used in solar thermal. And to be able to go to higher temperatures like 700 Celsius, we need to look at compatibility of structural materials with different molten salts. We form all kinds of phases on the oxide scale. And the key point in this is how the molten salt cares about the moisture, for example. So we need to do Courbet diagram calculations, and we are now doing this quite high temperature calculations and trying to get access to this kind of Courbet diagrams. And this is ongoing with Hanyang University, is a collaboration. I'm actually not going to talk in detail about this, but the last result is hydrogen effect. So we have used the PFP in a medium entropy metal, nickel, chromium, cobalt, and we are using it to simulate hydrogen diffusion. And what you noted is we're able to do 6 microseconds simulation. Typically with ab initio molecular dynamics, you're only able to do maybe up to 50, 100 nanoseconds of simulation. But also, this have so-called chemical short-range order. So we're doing this hydrogen diffusion in a pretty large supercell in order to study this medium range, chemical short-range order effect. Now, we do not know whether our prediction is correct or not. So at room temperature, it's about 10 to the minus 14 meters square per second. However, we do have experimental result for nickel single crystal. So same structure, FCC, but pure nickel, which is 5.6 10 to the minus 14 per meter per square per second in the 100 direction for nickel single crystals. And then there is another nickel-based alloy, 625, which is also a polycrystal. And they have a prefactor, which is 1.8 10 to the minus 7 meters square per second. We have a prefactor, which is like double that. And then it has an effective activation energy of 0.46 eV. For this complex alloy, we are 0.43. So this is not really conveying really accurate information because these are alloys and this is not same composition, but it's just to say it seems to be able to produce something that could be same. And then we have now used this to study the impact of the chemical short-range order on the diffusivity of hydrogen. And we see kind of like a factor of 2 difference in the hydrogen diffusivity at 400 Kelvin. And this is like a prediction from the simulation. And also in collaboration with Amita Trainer at MIT, she has found that this preferred network potential is able to reproduce zirconium hydride kind of the structure and different phases of that material, even though these multi-metallic systems were never sort of intentionally fitted in the original development. So I just like to sort of, in the last few minutes, sort of talk about something which is even newer than that potential, because we sort of developed, this architecture, and this is now commercialized into a product that seems to be pretty promising and is able to do microstructure. But what still feels really shocking this year, on the Pi Day, no less, is like for a whole week I was feeling a little bit depressed. I just feel something was off when I was just using this, and later I felt like it was very similar to the movies of alien invasion that we've seen. So I should give a name. I just replaced the L by an I. I call it AI invasion, because I feel there is just so much power that now these large data and these new networks can do. So there is this question of how far it eventually can go. And so this is actually a pretty alarming chart, I think, which is the percentage of electricity that is used for communication and computing. So the green is the data farms. The orange is our mobile phones, computers, and then this blue is what we use in the wireless communications. And so the prediction is that in 7 years, the whole IT sector would take 1/5 of all the electricity that's produced. So that means that it's going to compete for energy with humans. And there are many other things we need to solve, like climate change, right? So you can say that eventually it could be energy limited or data limited, right? Because there's just so much data you can, let's say language data you can get. But I was also involved in some other work, which is, I think, quite alarming when combined with that plot, which is that nowadays people are developing these energy efficient neuromorphic hardware. So in this case, what we have is a tungsten trioxide layer where we have a source and drain. And unlike typical semiconductors, where your dopant is fixed, here we are pumping proton across this phosphosilicate proton conductor in real time. So we're dynamically doping the tungsten trioxide and changing the tungsten from valence 6 to valence 5 and changing the electrical conductivity. So this is similar to the ionic channels in neurons. In neurons, we use sodium, potassium, calcium. So we have these ion channels, which changes the neurons and synapses, and that will give us the biological brain. But the question here is, comparing this kind of, you can say this is a miniaturized solid-state battery, proton solid-state battery, but we're using this impact on the electrical resistivity, is ultimately, how does this compare with biology? Now, biology, the action potential is typically only 100 millivolt, because biology relies on water, and water has a narrow electrochemical stability window. if you apply 1.2 volt, it's going to decompose into hydrogen and oxygen. And because of that, the action potential timescale is like a few milliseconds. So that controls the speed of our reflex and thinking. But in this particular device, we actually applied 10 volt across 10 nanometers. So an extreme, almost near dielectric breakdown electric field. And that was able to drive the proton across in a few, like 10 nanoseconds. Okay, so what we have demonstrated in this collaborative work with Bilge Yildiz and Jesus de Alamo is we have this device which is a few tens of nanometers in X and Y and 10 nanometer in Z, and we're able to kind of do this three-terminal device with 10 nanoseconds and a few femtojoule of energy. And in terms of time scale, the biology just cannot compete with this inorganic, silicon and proton-based device. So I just want to end up with this slide, which is, traditionally, we think only human can generate a scientific hypothesis, but we have done some experiments with ChatGPT-4, and there is actually quite convincing evidence that I think that it's actually able to make its own hypothesis. There's a lot of mistakes. It actually says a lot of nonsense because I think it kind of permutes the meaning of words, and it sort of sometimes randomly permutes words. But our feeling was it's also pretty creative. And I think sometimes scientific inspiration come out. Somebody takes a bath, or you're just dreaming in your when you're sleeping. So how human come up with scientific hypothesis is also kind of random and a lot of errors. But nowadays, I know, at Berkeley, you have been doing this automated experiments. The AI can actually generate hypotheses, but it can actually eliminate the wrong hypothesis by doing robotic experiments. And so nowadays, everybody is trying to develop this autonomous laboratories, and Berkeley has been really trailblazer in this. And so I think by combining hypothesis generation, which is typically associated with human behavior, and the ability to do experiments very, very quickly, I think there could be what I call a mass production of science, where you can have different AI beings are sort of doing this peer review, and also you're sort of transferring samples and sort of you're testing whether other materials labs material is really what they claim. So I really think there is a lot of potential in AI, but it's almost like scary because now all the human knowledge is sort of being taken by this GPT-4, and really is like very, very powerful. So I just sort of like to end with that note, and thank you for your attention.
Okay, wonderful. Thank you very much for this talk. We have time for perhaps 5 or 6 questions, and a lot of them have been submitted. So let's see how many we can cover. So there's a question from David Holek. Does it make sense to have better accuracy than the underlying data with respect to the claim of chemical accuracy of DFT being 100 MeV per atom?
Right. That's a great question, because we are now trying to, not we, but preferred network is trying to use the CCSD-T methods, but because those are quite limited to small molecules, so there is actually a question of what is the true data, because even experiment, even experimental thermochemistry data of measuring the reaction enthalpy and so forth, it also have an error bar. So I don't think it makes sense. Yeah, that's the point. Is I don't think it makes sense at this stage to be better than the chemical accuracy, because yeah, like our DFT data is worse than the chemical accuracy. So that's actually the point, is we really need to generate better ab initio data and then move on. But I do want to say that we are still lacking in long range interaction, and also we have been trying to fit potentials which are both depend on position and also the spin. So we try to develop this spin dependent potential, but we encounter a lot of difficulty in that, because even DFT have problem giving us energy surfaces that involve magnetic moments. I think for the next step, we do have to have better ab initio methods.
On that note, perhaps I can throw in a quick question of my own. Have you looked into or considered doing multi-fidelity training to incorporate, say, small amounts of experimental or R2 scan data?
Yeah, we're trying to do something similar to that. But I think, yeah, there is effort to making it more accurate, but there's also effort to sort of kind of compete on this curve, on this Pareto front as well. Because we can do up to 50,000 atoms now, but for some people that's still not big enough. So we try to kind of try to reduce the accuracy at some point. Like the previous question, maybe we don't need the 10 MeV per atom for some problem, but we need to have like a million of atoms.
Mm-hmm. Okay, next question comes from Salim. I hope I'm saying that right. How do TeaNet benchmarks compare to neural networks like FermiNet, Deep Erwin, as well as M3GNet?
I think we have done those kind of calculations. There's like a big supplementary materials. I think we are not the best in terms of accuracy. Like this 10 MeV per atom, many networks can do that. But I think the claim is that we're able to get 72 elements today, and this is a commercial product that's ready to go, and it has a very nice user interface. So I think that's the sort of, yeah. So we are not that accuracy focused at this point.
Okay, makes sense. A very related question to what you just mentioned, nice user interface and so on. Sergey Barabash is asking, is this potential free to use? What are the licensing terms, in particular for industry users? And how to begin using it? Does it require special compilation of lamps?
No. So this is a software as a service. So there is a GPU farm that you don't even see, and you just use this Jupyter notebook. And there is a 3 months free academic license. So if you're interested, you can just contact them, or you can talk to me. I can get you in touch with them. And they're very much now into trying to hunt for errors. So if you can actually point to places where this potential fails, I think they can give you some discount in the licensing. I think it's definitely going to be more expensive for industry. For academic institutions, I think if you can contribute to the error discovery, that I think you can lead to more favorable licensing terms.
Great, that's good to know. Then there's a question from Hui Zheng. Do you have the energy/force error statistics for different elements and material categories, such as alloys, oxides, sulfides, of your universal potential?
We have, but they're not published. So there is actually that's exactly what active learning is. Like you try to guide, how to generate more data in where it fails. So we have that data, but I'm not so up to the details of this at this point.
Okay. Next question comes from Felipe Gonzalez. He's asking, can this universal potential be used for high pressure calculations and prediction of new structures in chemistry at high pressure?
Right now, I doubt it, because in the diamond anvil cell, you can go to 300 gigapascal, and that would involve a bond length, which is like 50% shorter than the equivalent bond length. I think in our data set right now, it's not there yet, but I was just at Princeton, and we're talking to high pressure physicists, and now with this superconductor business. So I think this is actually one direction we're now moving into very much.
Okay, thank you. That's good to know. Slightly similar question from David. How about magnetism and magnetic phase transformations, such as steels and high entropy alloys?
Yeah, like I said, DFT itself has a problem with magnetism. We find that energy surface almost like non-differentiable everywhere. It's like there are a lot of transitions everywhere. So if you have a good, if anyone has a good ab initio method to get constrained magnetic moment calculations, I'd love to know. We've tried vast quantum espresso and so forth, and we still have a lot of trouble even generating this kind of open shell results.
Excellent. So it's about 11 a.m. now. There are unfortunately about 10 open questions still that we didn't get to. But if you look in this Zoom seminars chat, you can see the link to mathsci.org, where you can post questions, and perhaps we can get to them after this seminar. Let's all thank Julie again for this wonderful talk. And we'll hope to see you all next time, perhaps in roughly 2 months for a follow-up seminar.
Thank you, Janusz.
Thank you, Julie. Have a good day.
Bye.